Hi everyone. This lecture is meant to go along with the Orbits Lab, and I'll tell you when you should be doing parts of the Orbits Lab before you do this, uh, hear parts of this lecture. And we're going to cover Kepler's laws and binary star orbits and linear orbits. And this will be lots of practice with gravitational potential energy, which we covered last lecture. And so hopefully you have that formula handy. Okay, let's start with do now. See if you can use the equation for gravitational potential energy to show that the total energy of a satellite in circular orbit is given by this expression. So I want you to pause the video, try that yourself, and then I'll show the solution. Okay, pause the video. Okay, hopefully you had a chance to try this yourself because it's really practice for you using this new expression for gravitational potential energy. First of all, this is a little bit of review, equating circular motion with the net force, sorry, MA, this is MA, and net force, and using circular motion. We solved for V, we've done this before. And plugging that into the equation for kinetic energy, adding the new gravitational potential energy equation, you can see that we do in fact get this expression for the total energy. And another interesting thing to notice is that this first term, which is, if you follow it down, this is the kinetic energy term. The magnitude of this is half of the potential energy term. So apparently for anything to be in circular orbit, like a satellite around the Earth, the kinetic energy is half of its gravitational potential energy. Okay, so the next thing I want you to know is Kepler's laws. And Kepler was Johannes Kepler was really interested in astronomy, but actually he got most of his data from his mentor and then analyzed it for several years and came up with some general patterns in the data about planets orbiting the sun. And what he found, first of all, is that the path of each planet around the sun is an ellipse, with the sun at one of the two foci. So this is true. I mean, I think I mentioned this, that every orbit in the universe is some kind of an ellipse, maybe a circle, but generally some kind of ellipse. And I mean, unless there are several gravitational objects affecting it, I guess that wouldn't always be true. Yeah, if there's just one object orbiting one other object, it's always going to be an ellipse. And then the second thing he found, and I don't think he said it exactly this way, but if you look at a line from the planet to the sun, it's sweeping out equal areas in equal times. And let me show you what this looks like on a simulation. Okay, so here's an animation showing the Earth going around the sun. Clearly, they're not to scale, but what's interesting here is it's showing the arc of the motion of the Earth and then showing this area represented by the colored region between the Earth and the sun. And what it's showing is that the Earth is sweeping out equal amounts of area in equal amounts of time. And over here, that's kind of illustrated by these bar graphs where the area accumulates in the bar graph, and you can see it always comes up to the same level. Okay, and we can look at a different planet, Venus. Again, very circular. All of the planets are very circular, except I think Pluto. Let's see how Pluto looks. Okay, so Pluto's a little bit more elliptical. And you notice that when Pluto gets closer to the sun, the planet Pluto has to go faster to sweep out equal areas. And that's the idea. And this is actually the same idea we looked at in that Hewitt video about conservation of energy. It's the same idea, or the forces, stronger forces near the sun, weaker forces farther away. It all gives you the same result, which is that an angular momentum being conserved and energy being conserved gives you the result that the planet has to move faster, closer, and slower, farther away in this elliptical path, and that results in sweeping out the same area in the same amount of time. Still, we could look at something really extreme like a comet. And you can see the comet has to go really fast when it gets close to the sun to sweep out the same amount of area. So that's Kepler's second law. Kepler's third law says that the ratio of the periods of two planets orbiting the same sun squared is equal to the ratio of the radiuses of their orbits cubed. And this is not only true for two planets orbiting the same sun, it's also true for two moons orbiting the same planet, or what else? Two satellites orbiting the same Earth, any two objects orbiting the same other object. And let me show you the derivation of that. Kepler didn't derive it, he proved it just from the data, experimental data, but it can be proven using Newton's second law. And I believe Newton proved it actually later. Here's the derivation of Kepler's third law using Newton's second law. So you have two planets in circular orbits, so you can write this equation for circular motion. This should look familiar to you by now. Some things cancel out. And we also know that velocity is circumference over period. Make that substitution. You should try this yourself. You should be able to do this yourself. And then you get this equation here, which says that the radius of planet 1 cubed divided by the period of planet 1 squared is a constant. And if you do the exact same procedure for planet 2, you get the same equation for planet 2 equals the same constant. In other words, that's kind of a universal constant for this system where any planet, this ratio is going to be equal to this constant. And so then you can set this ratio equal to this ratio, and that gives you Kepler's second law. Okay, now before you go on in this lecture, you should do your orbits lab up through, including at least to activity, finish activity 4. And what you're going to find by the end of activity 4, hopefully you will have derived Kepler's third law. Okay, then you can also go on and do activity 5, but don't do activity 6 until you hear the next part of the lecture. So go up until activity 4 or 5, and then come back to this lecture. Okay, so if you're listening to this part of the lecture, you should have already finished your orbits lab up through activity 5. And when you're starting activity 6, you should be watching this lecture first. This is about binary stars. And there are many, many binary stars in the universe. In fact, astronomers have told me that there are probably more binary stars, double stars, than there are single stars. A lot of stars we see look like one star, but they're actually two. For example, in the Big Dipper constellation, this star we call Mizar is actually Mizar A and Mizar B orbiting around each other. And Mizar A is a double star itself, and Mizar B is a double star. And plus there's another one far away called Alcor, which is orbiting around both of them. So this is a kind of a double dance of these stars. Incredible. Let me show you what that looks like. Okay, I'm going to this simulator that's linked in your orbits lab. All right, here's the simulator, and we'll go to the double preset. And this is what a double binary looks like. So that's pretty cool. Let's look at this example of a binary problem, and you're going to do something just like this in your lab in activity 6. Okay, so this isn't a double, this is just a double. It's a binary star, which means two stars, and they're both orbiting around their common center of mass. So actually the orbit will look like A orbiting like this, and B orbiting like this, and I drew that down here. They're always going to be on opposite sides of the center of mass, otherwise the center of mass would move, right? So they've always got to be on opposite sides of each other. So you would also expect that their angular speeds would be the same. Okay, so mass A has a mass of 60, mass B mass of 30. The total distance between them is 300. And hopefully you've completed the lab to this point, so you know that in the simulation G is 10,000. I'm going to use that in this one so that I can actually simulate it when I'm done. First step is to find the center of mass. So it's not given, I just know the total distance. So figure out the center of mass. You could use the center of mass equation. You could also use torques, which gives you the same equation. So you could think of it kind of as a balancing of two objects on a pivot, although of course it's not. And then once you have the center of mass, that gives you the radius of star A from the center of mass and star B from the center of mass. Then you can do circular motion, and this is where this is kind of different from what we've been doing, because you can see that the radius for the gravitational force is RA plus RB. That's the distance between the two objects. But the radius for circular motion is just the distance from the center of mass to the object. So for object A, this is the equation. We can solve for the velocity of A. It's 18.3 maybe meters per second. I don't know. There are no units in this simulator, so it's all kind of a alternate reality. And then you could do the same thing for B, and you could solve for their angular speeds. And what's interesting is that you'll find that their angular speeds are exactly the same. In fact, once you know the velocity of one of them, you could just use not conservation, but the fact that their angular speeds are the same to solve for the velocity of the other one, and you get the same result. Okay, now I'm going to show this system in the simulator with these numbers. Okay, here I've set it up with the two masses in the problem and the separation of 300 and the velocities that we determined, and the simulation looks like this. Okay, that's not what we expected. Pause your video and figure out what went wrong. Okay, so hopefully you noticed that in order for them to keep their same center of mass, they have to be going in opposite directions from each other. And you can see they're always staying across from each other with the center of mass right here. And both of them are making perfect circles. So that's what we were aiming for, is circular motion of a binary star system. Okay, so this last question is about a linear orbit. And let's see what that looks like. Okay, here's the problem. Two stars of equal mass are 600 units apart. So minus 300 plus 300 equal mass, and no initial velocity. And what will be their speed when they're 200 units apart? Let's just see what this looks like. Okay, that's what we call a linear orbit. So this example problem is going to help you do activity 8. And activity 7 is kind of similar. It's also same kind of setup with energy, but it's to find escape velocity. Let's look at this problem, linear orbit. Okay, so to solve this problem, we're going to use conservation of energy. The energy before they start moving is all potential, and there's only one potential energy term. That's a common error. People think there's one potential energy term per object, but actually there's no potential energy unless you have two objects, because that has to do with the gravitational attraction of those two objects. So there's one potential energy for both of them, and then there's a kinetic for each of them, and then there's a final one potential energy for both of them. Sorry, this is initial, and then when they get to the point where they're 200 units apart, they both have kinetic and they have potential together. Okay, that's the way I should say it. So then we put in the terms for each of those things and solve for the velocity when they're 200 meters apart. We have the final separation and the initial separation, and the velocity turns out to be 100. Okay, let's check that in the simulator. Estimate the velocity by letting it go and then stopping it right here. And then the time is 5.6, and I'm going to let it go until it's like another, I don't know, this is what, about 40 from the grid line, so maybe 40 on the other side. Okay, so that's 6.4. So do the calculation and see that distance over time is close to 100, which is what we calculated. Okay, that's it for today.